All right, good morning. So welcome to the department's Warren Seminar Series, and which is made possible by a generous gift from Alice Warren. And today's seminar is quite special because we are here to honor the legacy of Ioannis Vardoulakis, who was a former faculty member of the University of Minnesota, who tragically passed away 9 years ago at too young age of 60. Ioannis obtained his diploma of civil engineering in structural engineering from National Technical University of Athens, and was awarded the Doctor of Engineering with the highest honors from the University of Karlsruhe in 1977. He joined the University of Minnesota in 1980 and quickly rose to the rank of professor in 1987. Ioannis was a towering figure in the field of geomechanics. He made major contributions in the modeling of geomaterials, geohazards, and geotechnical processes. Ioannis pioneered bifurcation theory to study localized failure phenomena in geomaterials. And he left a lasting imprint, not only at the University of Minnesota, but also in the worldwide community of geomechanics. And this brings me to today's speaker. So it is my privilege to introduce the 2018 Ioannis Vardoulakis Lecturer, Professor Jean Sulem, who is professor at the Ecole des Ponts in Paris. So Jean is director of research. He's the head of geomechanics Hermès at Laboratoire Navier and president of the French Committee of Rock Mechanics. He's a member of several advisory boards of scientific journals and is an associate editor of Rock Mechanics and Rock Engineering. And John earned his diploma in civil engineering in 1981, and let me use his French title, ingénieur civil de l'École nationale des ponts et chaussées. And in 1983, he obtained a PhD, again, doctor ingénieur de l'École nationale des ponts et chaussées, a thesis entitled, now I'm going to translate in English, Time-Dependent Behavior of Deep Tunnels. And in 1984, he received an habilitation à diriger des recherches for his study of bifurcation phenomena in rock mechanics. And habilitation is an European degree which gives the right to advise PhD candidates. So his research interests are related to conceive modeling of geomaterials, experimental rock mechanics, thermo-hydro-mechanical behavioral geomaterials, with application to tunneling, petroleum engineering, deep geological storage, and fault mechanics. The connection with Ioannis is that for almost 25 years, Jean worked very closely with Ioannis. They published 2 books together and numerous journal and conference papers. So it's a fitting tribute to Ioannis to have one of his close collaborators giving the lecture today. And before giving the podium to Jean, I would like to also mention that Jean is a French concert violist. He has studied in the Conservatoire de Paris with Serge Collot. He has played in the Ensemble Contemporain directed by Pierre Boulez, and he founded the Rosamond Quartet in 1981, and is still an active member today. So please join me in welcoming Professor Jean Sulem.
Thank you, Emmanuel, for this nice presentation. Good morning, ladies and gentlemen. It's a very great pleasure for me to be here, and a great honor to give this year the Vardoulakis Lecture. I would like to thank Professor Joe Labous for this invitation. And the topic of my talk today is the close interplay between weakening mechanisms that are active in faults and strain localization during seismic slip. So these weakening mechanisms, as we will discuss them, are from various origins, the presence of fluids, the thermal effects, but also in some conditions, also chemical reactions which can be responsible for this weakening mechanism. As Emmanuel said, I had the great chance to collaborate for almost 25 years with Ioannis Vardoulakis, starting in the mid-80s. I remember visiting him here at the University of Minnesota a couple of times during these years. And as it was said, Yannis was a pioneer in many domains of geomechanics and brought important contributions. And one topic that he liked very much was the interplay between the microstructure of a material and the strain localization phenomenon. He was one of the first to put in evidence that strain localization developed in relation with the microstructure, and introduced concepts of what is called higher order continuum mechanics, or continuum models with microstructure, especially Kucera Continuum models in the domain of soil mechanics. And just a few weeks before his tragic accident, during the summer 2009, Yannis was working on a new book with a comprehensive view of Kucera theory. You remember that it has published this seminal paper with Hans Mühlhaus in '87 in Geotechnique on the shear band thickness of granular material, and since then Kucera theory was used by many researchers and groups. Yannis was revisiting all the concepts, also bringing some clarification to some notions like coupled stresses or non-symmetric stress tensor in relation with the mechanisms at the contact of the grains. And 9 chapters of this book were almost completed when he had this sudden accident. And with his family and some former co-workers of Yannis and also some PhD students, we thought that it's a major work that will be useful to the scholars, to the researchers, to many people. And so we prepared together with Eleni Girolimatou, who was a former PhD student of Yannis and who is now in Chalmers University, Yannis Stefanou. He was a PhD student at that time. This is a picture taken in the Acropolis in Athens. Yannis Stefanou, who is in my group, Manolis Veveakis, who is now in Duke University, and myself, we prepared these lecture notes, and they have been published by Springer and just appeared a few weeks ago. So I am glad that this work is now published. So the topic today is related to fault mechanics, and I would like just to recall the multiscale framework when dealing with fault mechanics problem, and the schematic description as, for example, in the paper on Bension and Samis. If we look a fault at a regional scale, typically of the order of few tenths of kilometer, it appears as a network of oriented fractures of the Earth, which is responsible for the stress reorientation with respect to the far-field tectonic field, and which accommodates the long-term tectonic deformation. Now, if we look at this network at a more local scale, typically a few tenths of meters, we generally identify some zones of deformation bands, which are surrounded by damage zone. And if we look at these deformation bands even closer at the centimetric scale, we generally identify inside these deformation bands zone of very narrow slip concentration with a thickness smaller than 1 millimeter. So when dealing with fault mechanics problem, we have to deal with these various scales. And today, we will concentrate more precisely on the small scale, trying to understand how the multiphysics processes can influence this stress localization phenomena in narrow slip zones, and how this can affect the slip process itself. So this is an example of the punch bowl fault as documented in the paper of Chester and Chester. I take here one sentence of their paper The core of the fault consists of an ultracataclysite layer of shear localization that we see here, with a thickness of centimeter to tenths of centimeter. The scale here is 10 centimeters, so on this picture we see about 20 centimeter. And we identify here, the authors identified a single planar slip surface that accommodated several tenths of kilometer of slip. Actually, if we look more closely, this is not a surface, but rather a zone. This is, for example, documented in an outcrop of a fault in central Italy. I took this picture from the paper of Colettini, where this slip zone, which is called PSZ, is principal slip zone, is seen here. You see the scale, this is 500 microns. So the thickness of this principal slip zone is actually few hundreds of microns, and it has accommodated 5 to 10 kilometers of displacement. This is what is observed from exhumed fault, but same observation is made in deep drilling programs into active faults. I have taken some examples here of large earthquakes with magnitude bigger than 7 in Kobe in Japan, the fault system of Nojima, Chichi in Taiwan, the Chilungpu fault, Wenchuan in China, the Longmengshan fault, and all the observations from the drilling into these faults evidence that the thickness of this slipping zone is of the order of 1 millimeter. So slip is actually localized in extremely thin zones. We know that an earthquake is triggered by an instability, a frictional instability along a pre-existing mature fault. So schematically, I represent here a fault as a long layer embedded into a crustal block, and which is, the crustal block is remotely loaded by a normal and a shear stress. And this system is analogous to the so-called spring slider system, which is used in seismology, of a block which is sliding over a surface. And the stiffness of the spring here is representing the elasticity of the crustal block. And this system is used in seismology since Bayerle to understand the stick-slip phenomena and the seismic cycle, because we know that such a system can give rise to instability in the form of stick-slip movements if the rate of the weakening of the frictional resistance at the interface is stronger than the stiffness of the spring. This is also known in other domains, like, for example, in experimental rock mechanics, we know that we need very stiff loading frame in order to control the post-peak behavior in a compression experiment. So we distinguish between the stable slip, which correspond to aseismic or creep movement of the fault, and the aseismic and the seismic movement, which is triggered at the unstable state here, where the softening rate here becomes strong enough. So we understand from this very schematic representation that a key factor from the onset of earthquake is actually the mechanisms of weakening of the fault. So the softening of the shear resistance of the fault zone is responsible for the nucleation of the seismic slip. And in the following, I will give some examples of major weakening mechanisms that can be responsible for this softening behavior. What is important is that this slope here does not control only the onset, but control also the evolution of the seismic slip. This is why today we focus our attention on these weakening mechanisms. I would like to emphasize the fact that during seismic slip, most of the weakening mechanisms are from thermal origin. And for that, I would just recall the energy partitioning during an earthquake. So the potential energy, which is mainly the elastic energy which is stored in the crust, is released in three parts. First part is the radiated energy by seismic waves. This is what we measure with the seismometer, or what we feel as humans, or what the structures feel. And we see, and this can be empirically related to the magnitude of an earthquake, and we see the tremendous amount of energy which is released in very strong earthquakes. The second part is the fracture energy, which is the energy which is associated with the expanding the rupture zone. And the third part is the thermal energy, which is the part of the frictional work, that is the energy required to overcome the friction of the fault, which is converted into heat. And from field observation, it was observed that this is actually the greatest part of the released energy. More than 90% of the mechanical work is actually dissipated into heat. This is why it is expected that thermally induced weakening mechanisms are of major importance. So we will list few of them, few of the important ones. And first, the mechanisms related with the ubiquitous presence of fluids in fault zones. The core of the fault zone, which is made of this very granulated gouge, has a very low permeability, so that during a very rapid slip event, the fluid and the heat are trapped inside the slipping zone. And due to the fact that the thermal expansion of the water is much higher than the one of the grains, the water is actually caged into the solid skeleton, and this induces an increase of the pore pressure. So this is known as thermal pressurization of the pore fluid, which is due to frictional heating. These mechanisms of thermal pressurization of fluid is also important in other domains of geomechanics, for example, in deep repository of radioactive waste, for which we know that these are exothermal materials which hits the rock mass. And for example, in Europe and also in France, we have some projects of repository in shale or in deep clay rocks formation. The problem of putting hot waste into a rock mass with very low permeability can induce an increase of the pore pressure that we have to pay attention to in the design. So of course, thermal pressurization is a mechanism of weakening because the actual effective stress is decreasing, so the shear resistance is decreasing. Some other thermally induced mechanisms can affect directly the friction coefficient, and among them the flash heating, which is occurring at microasperity contact, and due to stress concentration, intense heat generation, and for rather shallow conditions, we can even have local water vaporization and induce local pressurization. Other mechanisms of reduction of the friction resistance linked to the lubrication of the fault plane, either by the formation of a macroscopic melt layer, jellification of wet silica-rich fault zones, and also the production of very small particles, nanoparticles, due to the wear of the asperities, but also of tribochemical reactions. I will discuss this point a little later in the talk. If the temperature rise is sufficient, the onset of chemical reactions can be triggered in the form of thermal decomposition of minerals. typically dehydration of clay minerals above a few hundreds of degrees, and decomposition of carbonates above about 700 degrees. And this type of reaction, dehydration of clay minerals or decomposition of carbonates, will release an additional fluid phase into the system because dehydration liberates water and decarbonation liberates CO2. So this source of fluid at high temperature will contribute to an increase of the pore pressure. Also, thermal decomposition induces a reduction of the solid volume. So in competition with this increase of the pore pressure, we can have an increase of porosity and of permeability that will be in competition with the pressurization. From the energetical point of view, these chemical reactions are endothermic, which means that part of the frictional work is actually used in the reaction. And the consequence of that is that it will limit the increase of temperature. As we will see in some simulations, the temperature will remain on the threshold temperature at which the chemical reaction starts. And this has been argued to be a possible explanation of the greatly debated question, what is called heat flow paradox, the fact that along large crystal fault, we don't see large melted zone, and we do not see high heat flux anomaly. So one possible explanation is that the temperature rise, because it is limited due to chemical reactions, is not as high as could be expected. And all these mechanisms have also been observed and discussed in the context of landslide mechanics. I would like to see some examples. This is an example taken from a paper on high-velocity friction test on carbonate samples. And we see here, it's called DZ here in this picture, decomposition zone. We see the scale 50 microns, so it's about 50 to 70 microns of this zone where decomposition of carbonates has occurred. We see this different microstructure, more porous zone as compared to the wall. And yes, this is here a zoom of this zone. But this is also seen in nature, in exhumed fault. It's the same example as before of this Spoleto thrust fault in central Italy. But now looking in the principal slip zone, we look what is designed as number 5 here, this very small zone. And the authors have documented, you see this calcined crystal showing decarbonation, these bubbles. Also the fading boundaries here are the results of decarbonation which has occurred during seismic slip. And this is some evidence with these irregular pores of dehydration of clayey materials. So it's also seen in exhumed faults. So if we summarize these processes, we have rapid slip, which produces frictional heat, causing increase of temperature. On one side, we have thermal pressurization of the pore fluid, pore pressure increase, which is a mechanism of slip weakening. If the temperature rise is high enough, we have mineral decomposition with a release of an additional fluid mass contributing to more pressurization of the fluid, so to stronger weakening. But on the other hand, in a competing effect, Sulem volume decrease, an increase of porosity and of the diffusivity, which can cause a decrease of the pore pressure. And this is a mechanism which can induce slip strengthening as opposed to this one. And from the temperature, the heat which is consumed in the endothermic reactions will inhibit the temperature rise. So I would like to show an example of a simple modeling. So we take here a layer under an imposed slip at a typical seismic slip rate of about 1 meter per second. The layer is long enough so that we can assume that the length scales in the direction parallel to the fault over which the thermo-hydro-mechanical fields vary are much larger than in the direction normal to it. So we can consider the variation only in the direction z, which is normal to the fault, and with time. And the governing equations are the following. The mass balance for the fluid, which gives the pore pressure, diffusion, and generation equation. In the right-hand side, we recognize the term for the fluid diffusion. This is a source term, which is the thermal pressurization term. Lambda is the coefficient of thermal pressurization, which in thermopore-elasticity is expressed as in the numerator here, the difference between the thermal expansion coefficient of the fluid minus the one of the porous medium. And in the denominator, we have the sum of the compressibility of the porous volume plus the compressibility of the fluid. And this coefficient has typical values of between 0.1 to 1 megapascal per degree. So this is the source term. If we have chemical reactions, we have fluid production, which is an additional source term. And this is the term corresponding to the inelastic porosity change, for example, due to solid decomposition. We have the energy balance. We assume here that all the frictional work is converted into heat. So we recognize here the heat diffusion term, the source term, which is the frictional heat. And here with the sign minus, it is the heat consumed into the chemical reaction. And delta H naught is the enthalpy change of the reaction. So this is an example of computation. We consider a thin layer of 5 millimeters submitted to a slip of 1 meter per second. We have the temperature rise here. After 1 second, it reaches the critical temperature for which the decomposition of carbonate is possible. And you see that after that, the temperature stays almost on a plateau. For the pore fluid, we have the first phase, which is the thermal pressurization of the pore fluid. Then when the reaction is triggered, we have an acceleration of the pore fluid increase. And because it is in competition with the increase of the porosity and of the permeability, it reaches a maximum, a peak, and then decreases. And we can translate this in terms of shear resistance with the initial weakening, stronger weakening when chemical reactions occur, and then a re-strengthening. And just to emphasize the effect of chemical decomposition, if we perform the same computations without, and this is the curve here in a dotted line, without considering decarbonation, we see that the temperature rise can be much higher, reaching values for which melting of the rock would be possible. In all this analysis, we see that a very important parameter is actually the thickness here of the shear zone. We have observed in the field, in the experiments, that the shear is localized typically in zones of few hundred of microns, and it is there that the frictional heat is actually concentrated. So the thickness of the shear zone controls all the dissipative phenomena. So it has a major role in the energy budget of the system, control the feedback of the dissipative terms. it has also an important role in the rupture propagation mode, as stronger weakening is expected for thinner shear zones. And the width of this slip zone will evolve in time because stronger weakening will favor a more localized zone, whereas heat and fluid diffusion will tend to broaden it. So localization here is a whole process where localization and possibly delocalization is also possible. This we'll see in some computations later. So the actual thickness and the evolution of the thickness of the localized zone should come from a proper localization, strain localization analysis, and for that we have to have the good tools. We know also from the pioneering work of Yannis Vardoulakis that a major drawback of the classical continuum theories for rate-independent materials is that it leads to an infinitely small localized zone, which corresponds to a slip on the mathematical plane, which is non-physical, and doesn't correspond to the observations also. And this can be traced to the absence of a material length in the constitutive equations that could limit the actual thickness of the localized zone. At least the grain size is a limiter for the localized zone. And then the remedy are known, either going to introduce viscous term, it's called viscous regularization, so considering rate-dependent constitutive law or the framework of viscoplasticity, or resorting to generalized continuum theories, Kucera, higher order grade, where we will introduce information at a lower scale that would limit localization. So in the following, I will say some words on the Kucera continuum because this is what we have used in the analysis. The idea of taking into account the microstructure in the description of the material can be traced back to the work of the Kucera brothers, their book, Théorie des corps déformables, in 1909. Actually, there were two brothers, Eugène, who was a mathematician, and François, who was an engineer. And he studied, and he was also a professor at Ecole nationale des ponts et chaussées. And the idea of their work was to attach to each material point directions so that they describe the kinematics of the material point, but also the evolution of the directions which are attached to this point. So they have displacement and rotations. More generally, and this was proposed, for example, in the work of Ehringen in the 60s, 1960s, the idea was to attach to each material point a microvolume so that the kinematics of the continuum is described not only at the macro scale by the displacement of the material point, but also with the description of the deformation of the microvolume which is attached to the particle. And the Kucera continuum theory is the particular case for which this microvolume moves as a rigid body. We retrieve the idea of the Kucera that the directions, the fixed directions, which are moving or turning with the particles. So it's clear, and this was the idea of Hans Mühlhaus and Yannis Vardoulakis, but also before them in the 50s by Günther, that Kucera continuum theories were appropriate to describe the behavior of granular materials. However, in the very early applications of Kucera theory, it was a bit disappointing because as soon as the wavelength of the deformation mode is rather large as compared to the grain size, we find that the Kucera effects are negligible. So the applications fade away in some way until the 80s and the ideas of Yannis and Hans that it could be useful in strain localization analysis because indeed there is a strong interplay between the microstructure and the localization phenomena. So I would like to illustrate the effect of the Kucera terms in one example, which is the study of the stability of the undrained adiabatic sharing of a rock layer with a Kucera microstructure. If we take the problem of the stability analysis of undrained rock layer without taking into account the thermal effect, the problem for a classical continuum, the problem was addressed in a famous paper of Jim Rice when he was discussing the question of dilatant hardening. So, and later the same problem was also addressed by Yanis in the 80s. So in the work of Rice, considering a layer, an infinite layer, under undrained sharing, the important result is that instability is possible in undrained condition when the underlying drain system is unstable. In other words, at the peak of the stress-strain response for a drain in drain condition, this state corresponds also to instability in undrained condition for a dilatant material. However, as discussed by Yanis Vardoulakis a few years after, this mathematical problem is ill-posed because what we find from the stability analysis is that the dominant wavelength of the instability mode is infinitely small. So again, in a classical continuum, everything is localized in a zone of zero thickness, and the rate of growth of the instability in time is also infinite. So this is indication that, of course, there is the conditions for the onset of instability, but we cannot say anything after that. In the paper of Vardoulakis, Yanis introduced the effect of viscous term in order to regularize the system. Okay, so now in this problem, I consider Kucera structure, so have to have the good limiters and the good description for the microstructure, but I will also consider the effect of temperature if we have a shear which is imposed at a very high velocity. So the technique is, as proposed by Rice, to perform a perturbation analysis of the homogeneous solution. Perturbations correspond to material imperfection or disturbances of the loading system. And we look at the evolution of time of this perturbation. They can vanish, which indicate that the system is stable, or they can blow up, which indicate that the system is unstable. So I would like just to emphasize the additional terms due to the Kucera theory. When we write the linear momentum balance, we have not only the equations for the stresses, we have also the angular momentum balance with the equations for the coupled stresses and here the Kucera rotation. The fluid mass balance is not changed. We have here the source term of thermal pressurization, and this is the non-elastic term. For the energy balance, we have to consider the total plastic work with the work of the stresses, but also the work of the coupled stresses. And we take here the constitutive model that was proposed by Mulhouse and Vardoulakis, which is Drucker-Prager type of plasticity model for which the invariant for the shear tensor is enhanced, is generalized to account for the effect of coupled stresses. And R is here the internal length of the Kucera continuum, which is related to the material grain size. Okay, so when we perform the perturbation, we decompose the perturbation into Fourier modes. Lambda is the wavelength of the perturbation, and the solution in time is exponential. So we solve the problem in terms of S, which is the growth coefficient of the perturbation. If S is negative, it means that the perturbation vanishes. If we find solutions for which S is positive, we have instability. The first interesting result is that if now, because we have the effect of thermal pressurization of the fluid, if the dilatancy is not strong enough to compensate the thermal pressurization of the fluid, we can get instability even in the hardening regime. So the effect of the thermal pressurization is to have earlier instability. And the other interesting result related to the introduction of Kucera terms and the fully dynamic analysis is that we find that looking at all possible perturbation, at the instability, all perturbation with a wavelength smaller than some critical value are actually stable. It means that if the layer is thin enough, it will remain stable. Only the wavelengths which are bigger have a growth coefficient which is positive, but finite, and we have here maximum indicating that there is one particular mode which will develop faster than the other. So we will relate this to the actual thickness of the localized mode. I have no time to show all the details of this comparison, but I will show later on some numerical results that addresses this problem. And for conditions corresponding to a fault at seismogenic depth, condition of pressure and temperature, we take here 7-kilometer depth. And if we take a grain size of 1 to 10 micrometers, corresponding to what is the structure of the core of a fault, we obtain a localized zone thickness of about 0.1 to 1 millimeter, which is compatible with the observation. I won't show it in this talk today, but we have also enhanced this exercise by considering the decomposition, the mineral decomposition, chemical reactions, which is an additional weakening mechanism, which leads to more softening and then more localized. And as soon as the chemical reaction is actually triggered, then we find either smaller thickness of the localized zone, which is more of the order of few tenths of micron, which is also compatible. We have seen in one of the previous slides that we had the localized zone, and inside this localized zone, the zone where the decomposition was actually active. Now, the linear stability analysis is useful because it gives the condition of localization. We have here the thickness of the shear band at the onset of localization, but we cannot say more. We need to solve completely the fully coupled nonlinear problem using finite element to follow the whole process of localization. So this was done in a recent PhD student of one of my students, Adrien Rates, who is now doing a postdoc in Duke University. I would like just to show the result. Yes. So this is how the system softens in relation with the pore pressure increase inside the band and the temperature increase. All this is localized. Another interesting point is that we consider here a rate-independent constitutive law. As you know, in seismology, we use commonly what is called rate and state friction laws. So we introduce generally rate dependence of the friction coefficient, which we don't do here. We could, of course, but what I want to insist on is that even considering rate-independent constitutive law, we have rate effects because of the diffusion process. So if we consider a slip rate which is not too high, then the thermal pressurization effect is not strong enough to induce really softening. But the softening is more noticeable for faster shear rate. And this is linked, you see, to the shear band width, which becomes smaller and smaller for faster rates. And yes, this is illustrated here. So this is the same simulation as before with a velocity of 1 meter per second. And with a velocity of 1 centimeter per second, you see that the system is less localized, the pore pressure change is much smaller, and we even have a delocalization. So you see that it's a whole process, and this is softening, but it's so small that we don't actually see it. So what I want to emphasize here is the rate effect that we obtain through the diffusion process that control the localization. In the first part of my talk, I have mentioned that at some point of the slip process, if the temperature rise is strong enough, we can have chemical reactions. So the chemical reactions are actually the consequence of the seismic slip. But in some cases, it can be the cause of seismic slip. And I would like, in a few minutes that I have left, to discuss this problem when chemical reactions can be responsible for the onset of earthquake. If we look at this diagram from the paper of Green, we have here the number of earthquakes per year in log scale as a function of the depth of the epicenter. And we see this bimodal distribution, clearly a strong peak here corresponding to a depth of few tenths of kilometer, 20 to 50, which is the transition between the brittle and ductile part of the crust. And most of the earthquakes are actually nucleated in this part. But we see that at much deeper conditions, so for conditions for which pressure and temperature would be so high that brittle failure is actually precluded, we have earthquakes. And we have this other peak at about 600 kilometers depth. This is known as deep earthquakes. And these deep earthquakes have been recognized about 1 century ago, and it was a big paradox. How can we have earthquakes in a ductile regime? And this was explained some years ago, and many studies in the last 20 years about the effect of chemical reactions. So now we understand that between 50 and 400 kilometer depth, these earthquakes are due to dehydration reactions, so breakdown of hydrous phases, and deeper, between 400 and 700 kilometer depth, it's conditions for which we have phase transition of olivine to higher order polymorph to spinel. And this is accompanied by a change of the volume. And this is the mechanisms that can trigger an earthquake. However, this is called intermediate earthquakes. This is called deep earthquakes. They are different. Generally, these earthquakes are called tremors or silent earthquakes because they are occurring in rather long period of few days. These are much stronger and look like the shallow earthquakes. There are examples. For example, in 2013, in the east part of Russia, in the Sea of Okhotsk, there was a strong earthquake at a depth of over 600 kilometers with a magnitude of 8.1. And it was so strong that it was felt very far away, even in Moscow, which is 7,400 kilometers far away from the epicenter. There were almost 1,000 people who were evacuated because the shake was actually felt. And after this big earthquake, there were several aftershocks, also very deep at about 600 kilometers. And one of them was recorded as a super shear earthquake. Super shear means that the velocity of the fracture, which was, if I remember well, of 8 kilometers per second, is higher than the velocity of the shear waves. This is the case of super shear earthquakes. So very deep, we have these very strong earthquakes. But in the following, I will say a few words about the modeling of these intermediate earthquakes. So we take this example of antigorite decomposing in forsterite, anstatite, and water. So we have production of fluid phase, a production of denser minerals, a decrease of the solid volume. So even if the material has, at the beginning, almost no porosity, this reaction will cause an increase of porosity. We'll have a porous rock. And we can have actually two types of behavior depending on the condition of pressure. So below about 60 to 120 kilometers, so below pressure, which are between 2 and 4 gigapascal, there is a net increase of the specific volume of the fluid, which means that we have a net pressurization of the fluid because we have an increase of the porosity, but the amount of the fluid which is released in the system is such that we have a net increase of the pore pressure. So increase of the pore pressure brings the state of stress back in the brittle regime because the effective stress is decreasing. So in this case, when this is called dehydration and brittlement, and being back in the brittle regime, we understand that we can have instability and seismic slip. But if the pressure is higher, so at even higher depth, we have actually a decrease of the specific volume of the fluid. So in that case, we have actually a decrease of the pore pressure because the creation of porosity is such that the pore pressure is decreasing. So if the pore pressure is decreasing, which means that we have an increase of the effective stress. Now imagine the analogy with a porous rock, for example, a carbonate or chalk, very porous, under a very high confining pressure, we know that we have phenomenon of pore collapse. So this is what actually occurs here. We have the transition from a non-porous metamorphic rock to a fluid-saturated porous rock under an increasing effective stress, and this causes pore collapse, and thus, as a secondary effect, increase of the pore pressure, and then bring it back again the state of stress in the brittle regime. So in the two cases, for different reasons, we have this dehydration and brittlement. So I would like just to show one example of modeling for this particular case that we have derived in a recent paper in GGR. For this, we take some experimental data published on, by Reuter on serpentinites at various degrees of dehydration. These are triaxial tests. So this is the non-dehydrated rock, and at various levels we see that the yield surface is shrinking. So it's like in porous rock when we have a porosity-dependent yield surface. The porosity is, with increasing porosity, the yield surface is shrinking. And we see here from some micrographs given in this paper, starting from a porosity of almost 0, only 0.1%, the creation of porosity, and also we see big pores here, and also some new olivines, nanograins, along boundaries. For the modeling of that, we take a porosity dependency in surface. N is a porosity, and N depends upon the evolution of the chemical reaction. We took the experimental results from Ruther, and we have calibrated a CAM-clay type of yield surface, assuming associated plasticity. To describe the kinematics of the reaction, we consider a pressure-dependent reaction progress. So this is how the pore pressure is controlling the actual rate of the reaction. And this is the fluid mass balance. It's like before. We have the diffusion, we have the mechanical term, and this is the effect of the additional fluid phase which is introduced in the system. To study the stability, we, in a simple problem, we consider a uniaxial strain problem. So it's like a odometric condition. We imagine a slab which is going deeper. We perform perturbation analysis, and like in the previous result, what we obtain is that at the instability conditions, all wavelengths greater than some critical value are unstable. So again, we have some threshold. Here we did not introduce any material length. It's done with a classical continuum, but we have some competing length between the diffusion length and the rate of the chemical reactions. And this gives the control length of the instability. Again, from the linear stability analysis, we have just the onset of the instability, but if we want to follow the evolution, we have to solve completely the problem. This is the 1D problem, and this is what we have done. This is the initial conditions corresponding to a fault, to a subduction zone at about 100 kilometer depth. Critical wavelength of the instability is a few tenths of meter, and typical time scale we find of few days. So this is compatible with the observation of silent earthquakes. And okay, we see here on this plot, so how the yield surface is shrinking in due course of the evolution of the reaction. We'll see it again with localization, but it's a transient process, localization. We have delocalization when the reaction is actually completed. And the time scale for that is few days. So I come to my conclusions. We have seen the importance of multi-physics couplings in the nucleation of earthquakes and also in the control of seismic slip and arrest. We can develop robust numerical tools, and it's still under development, also to introduce the effect of other phenomena, chemical reactions, for example. Of course, all these models and also the parameters need to be constrained. This is why we need field data that we have from all the drilling program and also from advanced laboratory experiments. And there are, of course, many challenging issues, other physical couplings or weakening mechanisms that has been described in the literature in recent works. For example, macrobial activity, which affects the pore pressure and then also can affect the stability of faults, acoustic fluidization, so that remote earthquake could trigger instability because of the passage of the seismic waves, effect of phase changes. In the example of Kucera model that I have shown, we have considered one grain size that controls the Kucera Continuum. But we see that in due course of the sleep process, the grain size is evolving. So we have now one PhD student working in collaboration with Sydney University and with Itayenav, combining breakage theory for granular materials and Kucera theory, so that we are developing a Kucera theory with evolving material length. Also, not only breakage, but also chemical reactions makes the whole grain size distribution evolve, and this can affect all the softening process. So, and we have seen that all these problems are multi-scales, so various time scales, length scales have to be considered, and cross-scale couplings is a challenging issue, especially taking into account the heterogeneities at all scales with appropriate homogenization and higher order continuum theory. And to conclude, I would like to acknowledge all my collaborators, Nicolas Brantu in London, Nick Collins, who is a PhD student in Sydney and in Ecole des Ponts, working on the combination of Kucera and breakage theory, Itayenav, who is his supervisor in Sydney, Thomas Poulet in CSIRO, with whom we have developed the numerical implementation of Kucera and coupled processes for fault mechanics. Adrien was a PhD student, Yannis Stefanou in my group, and Manolis Veverakis. Thank you very much.
It's time to entertain a few questions.
Oh, I can speak probably loud enough. Oh, for this. All right. So I did not exactly understand why there are no length scales involved in a simple setting, because you have diffusion coefficients, you have viscosity, and you have Young's modulus, and you could construct length scales from that do not necessitate the use of Kucera.
Yes, that's true. And if we perform the stability analysis of a drain adiabatic with a rate-dependent friction law and with the diffusion term, this was done in the paper of Jim Rice,
right,
for example.
Right.
Indeed, there is a selection of a wavelength. Now the question is, what is the physical meaning of this rate dependency of the friction, of the frictional resistance itself? I believe that rate-dependent friction could be introduced, but it doesn't mean that we should neglect the effect of the microstructure itself. So what I've presented here is, my point is, even if I don't consider rate dependency, but I introduce what seems more physical, the effect of the microstructure, in a very simple manner here, just the grain size of the material. So the grain size and the diffusion process, this is sufficient to select a dominant wavelength in the stability. But, of course, we can now generalize this to more sophisticated friction laws, like rest and state. There are a number of teams now working on trying to understand what is the physical meaning of this rate part in the rate, because these laws are very universal, applied to many different materials, but they certainly involve different physical processes. And for example, the rate dependency could be related to shear heating at the asperities. So really, we have to look at a smaller scale physics to understand what are the good law at the macroscopic level.
All right, thank you.
Thank you. It's absolutely fascinating, but I'm interested in how this develops over time. Like an earthquake is a major release of energy. So this must start in one narrow area along the fault, which then changes the system. Is anybody doing any work on attempting to scale this to the mammoth releases of energy that occur in a real earthquake?
Yes, there are of course, groups studying the whole cycle, studying the mechanisms of nucleation. Generally, they are attributed to the increase of pore pressure due to compaction, slow compaction phenomenon, and then the triggering of the instability itself. And then what I have focused on here is the very small part where the slip develops. The numerical tools that we are developing at the moment should help to follow the acceleration and maybe the deceleration. Also, the question is how an earthquake stops. What are the mechanisms that makes an earthquake stop? Diffusion, restrengthening. What are the mechanisms for restrengthening? Obviously, it's a multi-scale problem. But we have to look at what happens at a small scale to be able to describe the whole evolution.
Any more questions? No, if not, please join me to thank the speaker.
Thank you. Thank you very much.